All right, let's wait. All right, so today we're going to look at Ceva's theorem, which is a very commonly used one in competitive math. Now here what it says, and B and CF satisfy the following constraint here, which is AF over FB, the first term, and then BD over DC, the second term, and finally CE over EA equal to 1, then we claim that the three lines here, they're going to be concurrent. They're going to meet at the same point here, and vice versa, right? So we're going to prove that if they are concurrent, right? So what we want to prove is if A, D, B, E, C, F are concurrent, in other words, they meet at point P here, then we're going to have this condition here, right? So how are we going to prove that? So one proof is using the area of property, the area property of the triangles. Now review that if I have, in this case, triangle here, I have a point D, AD here, and then the ratio here, the ADC triangle, the shaded area, right, over the big original triangle ABC is going to be the ratio of the base here, which is the CD, DC over BC, right? So we're going to look at this particular term. Let's look at the ratio of this triangle, yeah, which is the area of triangle. Okay, we're going to say this is the area of triangle ABD. All right, and the other one, I'm going to use the right-hand side one. That is, how about choose a different color here? All right, so I would have this ADC here, yeah. So the triangle ADC is going to equal to the ratio of the base because they share the same height, right? Share the same height here. This would be the height, and this is going to be the BD over DC. All right, let's write it down. It's going to be BD over DC. Now, notice that. Let's look at the other triangle here. From the P, we're going to have the same relation here because they share the same height. So in other words, this ratio here, the BD over DC, this ratio, yeah, is also the ratio of the another area, which is PBD over the area of PDC. Okay, so now why we're doing like two different equation here. Now the trick here is that for proportion, for the ratio, there's an important property. If, let's review from basic algebra. So if you have a quantity here, let's say A over B equals C over D, then the ratio is going to be the same if you do the subtraction or addition, right? So that's a fundamental property from algebra. We're going to use that. So here we're going to say that this is going to be equal to the difference of the areas. All right? The bigger one, this is the bigger one, this is the smaller one. So it's the area of ABD minus the area of PBD, and the ratio of ADC minus PDC. Okay, so what is the subtraction of the two area? Now earlier we say that the bigger one would be this one, right? Minus the smaller one. So the result is going to be the remaining one, which is this triangle here, right? So that would be the difference on the top, right? Let's write it here. That's going to be the triangle ABP, all right? And the difference here in the denominator, ADC minus PBC, ADC, which is this one, this big one minus the smaller one. So the difference would be this one, all right? So in other words, here we're gonna have the area of ACP. Okay, so that's good. So now in similar fashion, now we have calculated the area here for the middle one, right? Like for this one. Now we have it here, right? So now similarly for AF over FB, the ratio of this side here, AF over FB, now in similar fashion, you're going to know that that's going to be the ratio of these two. Okay, so in other words, AF, let's write it down here. I'm going to skip the steps, but you may want to derive it offline here. So I claim that that's going to be equal to the area of ACP over the area of wait, this may be wrong here. Should be this one. The difference would be this one. Okay, so it's going to be the area of CBP. Okay, now similarly for C over EA, for C over EA, right? So now what you can do here is, the smaller triangle would be this one, the ratio, right? The bigger one would be this one, and the difference, there's a bigger one, yeah, this ratio here, the ratio C over EA is going to be for the area of this one, yeah, and also smaller one, and then the difference here would be, let me write it here, the difference here would be this one. Okay, and that would be this one would come oh sorry, it's something wrong here, would be this one, I believe. Okay, so that would be the ratio. So let's write it down here. So ACE over EA, yeah, would equal the area here, or highlighted, it's going to be area of BCP over the area of ABP. Okay, so when you multiply the three quantity together, let's do that. Okay, so the left hand side is going to be the AF over FB times BD over DC times CE over EA. We're going to plug in the area ratio, right? So here would be ACP, the area of ACP over the area of CBP times the second one is going to be this one, right? So that's going to be the area of ABP over the area of ACP, and finally it's going to be the BCP over the area of ABP. Now notice that things would cancel, yeah? So look at here, we have C, BP, and BCP is the same thing here, right? The cancel. And let's change a different color here, yeah? So ABP cancel, and finally ACP cancel. So that's equal to 1. Alright? That's Ceva theorem. Now, we know that the other direction is also true, but we're going to skip the proof. Alright? Now, there is another proof. Now, in the previous session, we introduced a theorem, that's Menon's theorem, that says for a triangle, if you have a triangle and you have another straight line cutting the triangle as 3 different sides, kind of intersection point, D, E, F, then we're going to have this quantity here, which is AD over BD, BF over FC, and then CE over EA equal to 1. All right? So, and also the converse is also true. In other words, if you have 3 points, and then they have this equation here, then you claim that D, E, F are collinear. That is, they lie on the same straight line. All right? So here we're going to use this theorem to prove Ceva's theorem. Okay? How we're going to do that? Let's try it. All right? So now for the Menon's theorem, the trick here is to figure out, which is the triangle, which is the line cutting the triangle. All right? So let's look at that. Okay, so we're going to hold on. If we're going to use this as a triangle here, ADC as a triangle, right? ADC as a triangle here. Okay, and the line would be I have a line cutting the triangle. All right, so I'm going to use a different color here. Okay, so if let's say the line is this one, right? So notice that this line, this straight line cutting the triangle in 3 different points, that is point E, P, and B, right? So now we want to prove this, right? If they are now from the Menon's theorem, we have with this triangle, right? So what we can do is we're going to write it AE, let's say AE over EC. Okay, we're going to say A. So this is from Menon's theorem, right? So what do we have for this triangle here? So I'm going to have AE over EC. Okay, remember this, you just go the same direction, right? AE over EC, and then CB, right? CB over BD, right? That's the intersection point is B, right? So times CB over BD, and then times DP over PA equal to 1. All right, so that's first fact. Now if we change the triangle a little bit, let's change this triangle, and we can change the line. The cutting line is going to be here, would be this line, and this would be the line. Then we're going to apply Menon's theorem again with the new triangle and the new straight line. Notice that the 3 points would be what? This straight line cutting at F, P, and C, right? So similarly, we're going to use Menon's theorem. So what do we have? is going to be, we have AF over FB. Let's write it. AF over FB. And then the quantity here is going to be AF over FB. And then BC over CD. All right? So BC over CD and times DP over PA. PA equal to 1. All right? So we can do cancel certain term from these two equations, and it's better, let's say this is code 1, this is code number 2. So for number 2, we're going to flip, okay? Flip number 2. In other words, we're going to turn numerator, we're going to swap it, right? So in other words, from here we have FB over AF, CD over BC, and then PA over DP equal to 1. Okay, let's call this 3. Now we're going to what we're going to do, we're going to multiply the first one and the third one. All right, let's do that. So I'm going to be lazy and try to copy paste, right? So I'm going to have this one here, duplicate it, and I have the other one, which is the third one, right? So I'm going to duplicate this, multiply these two, that's going to equal to 1, right? Now, do we have cancellation here? Yeah, yes, we do. So let's cancel. So AE, we're going to keep this. We're going to PA cancel. DP cancels. We have BC and CB cancels. We have, let me see. So what we have is, we're lifting is AFFB. Yeah, we're leaving the, let me see. Okay, so we have everything else cancels. So we have A, E, E, C, F, B, A, F, and we have C, D, and then B, D equal 1. Okay, this is exactly what we're trying to prove, right? It's kind of upside down, which is fine. So we have AF, FB, AF, FB, BD, CD, BD, CD here, CE, EA. Okay, that's a proof, all right? Of course, we can flip it, right? If we flip it, it's become, these two are equivalent, right? So let's mark it, this is just, we have the proof. So this is the second proof where we use Manin's theorem to prove Ceva's theorem. Okay, so we're going to use theorem to prove a few interesting facts. All right, so notice that for triangle, there's some geometric, the median of any triangle. We claim that for the median of triangle, okay, they're concurrent, right? So what is that? So in a triangle, so this is a claim. For any triangle, the medians, right? The median lines, 3 median lines of a triangle are concurrent. Of course, the 3 medians, right? This is geometric center, right? So, so in other words, if I have a triangle here, and for the medians, you're gonna be exactly, this is the midpoint here, and this is gonna be, almost midpoint, and the other midpoint. Okay, so I probably didn't draw it very well here. Okay, so A, B, C, D, E, F. The median means what? Meaning AE equal EC, CD equal BD, and this one equal this one, right? All the midpoints. Now we prove that they're going to meet at the same point P. How do we prove that? Using Cevas, right? So here we're going to look at the ratio. What is the quantity here? We're going to be, what is AF? The quantity going to be, what is AF over FB, BD over DC, and CE over EA, right? Of course, everything is 1, right? So AF over FB times BD over DC times CE over EA. That's going to equal 1 times 1 times 1 equal to 1. Of course, by using Ceva theorem, they are concurrent. All right. So another one is the orthocenter, which is the attitude of the triangle are concurrent, right? So again, this is another claim. So let's copy that. Let's duplicate it. Here we claim that not the mediums here. We claim that the attitudes here, right? So here is the 3 attitudes. Of triangle. So how do we prove that? All right, so let's move down a little bit. All right, so let's draw it here. I have a triangle. Right, so attitude is going to be the perpendicular line here. Okay. Yeah. And this one would be somewhere here, hopefully. Is it perpendicular? Almost. Right? And the other one would be 3 attitudes, right? So I have A, I have B, C, D, E, F. Here, this is 90 degree, perpendicular here, perpendicular, and perpendicular. This is probably not quite yet. Let's draw it here, and that's going to be a little bit over here, right? Okay, that's perpendicular, right? So how do we prove they're concurrent here? They all meet at this maybe orthocenter, right? This is called the orthocenter center of a triangle. Now we're gonna look at the ratio here. Right? We're gonna look at the what is AF FB times BD DC times CE and EA. So we're going to prove that that's going to be equal to 1, right? So how do we show that? Now we're going to rely on similar triangles, right? So there are a lot of similar triangles here. So notice that for the 2 right triangle, if they share a common angle here, then they're similar. For example, let's say this one. This is the right triangle, and the other one. Let's choose another one here. They share angle A, which is the same. So the other one would be this one. Okay. So this triangle. Let's shift a little bit so that there are the two triangles here. They are similar, all right, because they share all angles are the same, right? So with that, you're gonna have a ratio here, so that is the sides are in proportional, right? So let's do that. So for example, what is AE? That would be AF, right? AE over AF is going to be equal to AB over AC. Okay. Now similarly, okay, let's mark that. So we have AE here, which this is AE here, right? AE, AF, we have this. Okay. Now let's look at the other similar triangle for let's change that. Let's cut this one, yeah, and versus okay, sorry here, this, let's redraw it here. Okay, and the other triangle here is change a different color here, and the other one would be okay, right, so the BFC here, right? Okay, so they're also similar. This is a similar triangle. Let's write it. Earlier, this is the triangle, and ABD is similar. ABD, which is a triangle CBF. All right, so AB over BC is going to equal the ratio of let's see, AB would be BD, and BC here, BC would be BF. Okay, so finally, for the triangle, let's say if I have the C as a okay, so let me see, sorry, this is get rid of that. Okay, so I have this triangle, and I'm going to have a similar triangle, which is this one here. Okay, they're similar. Okay, so which means in this case we're gonna have AC over BC. Okay, is gonna equal to CD over CE. Okay, so if you have three equations here, we're going to multiply them together, right? This is 1, 2, 3. So we have the quantity here. So if you multiply these three together, we're going to have AE over AF times BD over BF times CD over CE is going to equal to AB over AC times AB over BC times AC over BC. All right, so we have to flip. Let's flip this, okay, because this won't cancel, right? So what we need to do is we're going to choose this to flip. Okay, we're going to flip it. So sorry, we're going to we have to flip this term here. We're going to flip it. Okay, so flipping in order to cancel this, right? So AB over BC here, AB BC, we're going to flip it, right? So it's going to be BC and AB, right? And here BD and BF here, we're going to flip it, right? That's going to be BF over BD. Now let's rewrite this, right? Let's rewrite this here. It's just a flip, right? So let's just make it sure. Okay, let's move it here. Move it here. Okay. So we have this relation here. Of course, on the right hand side, we're gonna cancel, right? BC cancels. this is not this is AB. This should be B. Okay. Earlier there's a typo here, right? So AB cancels, AC cancels. That's indeed equal to 1. And is this the quantity we try to prove? We bet it is. We try to evaluate this, right? So we have AF, BD, and CE. A on the top, AF, BD, CE, and the other side is BF, and then DC, and then EA equal to 1. So that's a proof. Okay. So the claim here is that the orthocenter indeed is concurrent at this point, right? Using Ceva's theorem. Now, the third claim we're going to prove, of course, is claim 3 is the angle bisector, right? So here we're going to prove that here. Here, not the attitudes, but the angle bisector of a triangle are concurrent, and of course this is not orthocenter. This is going to be the incenter. So how do we prove this? Again, using Ceva's theorem, right? Here the triangle again ABC, right? ABC. The angle bisector here. Important property of angle bisector, let's say ABC. If this is D and this is angle bisector here, this angle equal to each other. So there's an important property that AB over AC is equal to BD over DC. So in this case, if you have another angle bisector, right? So for example, this is angle bisector. It's not drawn to scale. Okay, and the third one. Okay, so this will be in center here. This would be the I, right? So we need to say this is E. This will be F, right? So since this angle bisector here, this is also, oh wait, what's going on here? Okay. Right. So if this angle equal to each other, this is bisector, then the ratio here is CE over EA, right? So in other words, we have BC over BA is going to equal to CE over EA, right? And finally, let's look at the other angle bisector here, right? So the ratio would be this sides here, BF over FA, right? Let's write it. So we have AF over FB, in this case, would equal to AC over BC. If you multiply them together, right? So let's change the size here. Okay. Yes, this is better, right? And multiply them together. The left hand side you're gonna cancel, right? So everything is cancelled. The AB and this will cancel, BC and CA. So you have 1 equal on the right hand side would be BD over DC times CE over EA times AF over FB. Now by Ceva's, that's indeed they are concurrent, right? So that's as a proofs, all right? So all based on Ceva theorem. I think today we just covered the Ceva theorem and then some examples of using that to prove that there's geometric center, there's orthocenter, and incenter of triangle. They will meet, at same point inside the triangle here. All right. So I think that's it for today, and thank you for your time. And we're going to continue with this geometric theories